All right, then we can begin this small lecture on in the Founders Make Tech at Lunch series. We have a few presentations, special presentations about energy cost reduction for large and medium companies, also smaller companies, because energy cost reduction is something that is very interesting at the moment, especially with these prices that keep rising. For the first lecture in the series, we have one by my research group, Air Leak SLAM, online detection of pressured air leaks in industrial environments using passive and active ultrasonic sensing. Before we start, I would like to ask everybody to turn off your cameras and mute your microphones. And if you have questions, you can put them in the Q&A chat box. And then after the presentation, we will hold a small Q&A session in which I will answer the best questions. And also this will be recorded, and you can also update the slides after the presentation if you want those. All right, then we can begin. Pressured air leaks. We, a while ago at my research group, we got wind of the possibility to detect air leaks, because I'll look later into that, but we do a lot with ultrasonics. And we noticed that we could detect those air leaks, and then we got into thinking, okay, what are the numbers behind this? Is it useful to detect these air leaks? And our market study said that if you look at the numbers on a European scale, that two nuclear power plants are running for a full year just to power those air leaks. So the energy wasted by those air leaks equals the energy that is generated by those two power plants. And that might seem like a lot, but that's also because pressurized air leaks are almost everywhere. It's not just large gas companies that have these leaks, because pressurized air is present almost everywhere. In HVAC systems, you have piping with pressured air running through them, but also in hydraulics at the pumps, they can also have like small leaks. But indeed, also the large piping systems, for example, in the harbor, you have factories with kilometers of pipelines. All those pipelines can have these small leaks. And a small or a medium-sized company can lose up to 17,000 euros annually by these leaks. And a large company may lose up to 80,000 euros. And I did small research before the presentation to make it a bit more tangible, but 80,000 euros is quite a lot. So if you would save up that money by fixing all your leaks, that would give you the possibility to order 16,000 pizzas and Domino's on Tuesday for your employees, which you will certainly enjoy, or you can be a bit more selfish, and it's also the price of an Audi A7. What you do with it is up to you, of course. And then, of course, the accumulated European loss would be about 218 million euros a year. And then the more interesting thing behind these numbers is that this market study was done a few years ago when the energy prices were a lot lower. And I went to the website of the VREG and to get a more accurate sense of these numbers. And yeah, you can see that starting in 19, when we're comparing the numbers of 2019 to the numbers now, they have increased fivefold. So that's even more out of 8 seconds for the board. So it's important that we can we can localize these air leaks and that we can fix them when they appear, and preferably as fast as possible. Now, these air leaks, they are wind going through a small opening. basically. And we know that wind going through a small opening creates a noise. If you whistle, it creates a pitch. If you take a flute, it also creates a pitch depending on the size of the hole you create with the flute. For these air leaks, this is no different, but because the leaks are very small in size, the pitch is very high. And this then comes into the territory of ultrasonic sensing. So smart people came up with the idea, okay, can't we design sensors to detect these air leaks using this ultrasonic footprint that these leaks emit? And we have systems on the market, for example, the SDT270, that is a cheap option, but that's also a bit cumbersome because you have a small microphone that you have to scan the entire pipeline with. That's not so useful if you have the 2 kilometers of pipeline in your factory. And then you have other systems that you can use at a distance. For example, the UA systems, that's UE systems, that's a bit older, but it's still around. Then you can scan from a distance. Or there are also more recent systems like those by FLIR that actually create an acoustic camera. So you have a microphone array that can exactly pinpoint the locations, and then an operator can walk around your factory and pinpoint the locations of these leaks, which is good. But yeah, it's still extensive manual labor because one operator still needs to walk around the entire plant. And if you have a site like BASF or something with extensive pipelines, that can be quite a number of steps during the day. And even though it's healthy, it's quite time consuming. So we as a ultrasound research group have also a lot of background in this field because at Coltis Lab we've been designing ultrasound sensors for over a decade, but mostly active ultrasound sensors. For example, our ERT sensor. Maybe some people present here have done some projects with us that use this technology. So we can use this. It's based on the bats. So actually, it's a digitized version of the bat, and we can put that on robots or on boats to make them navigate autonomously or make them perform several tasks. But a part of this sensor, the microphone array, is also can serve as an acoustic camera. So that got us thinking like, okay, maybe we can also do this. We can do the same. We then went ahead and did this. And a while ago, we presented at a conference our own interpretation of a system like this, where we took a VR glasses, the HTC Vive Pro 2 headset, fitted it with a circular microphone array around one of the lenses, and that would allow for an operator to put on the headset, walk around the factory, and see in an augmented view where the leaks are located. We have a small video demonstration of this. I have here also in my slides. It's a video version of the presentation we did at the IEEE Sensors conference a few weeks ago, or at least one of my colleagues went over there and did the presentation. I will go to the more relevant part. So here you see a close-up of the system, where you then see like the microphone array that is around the lens. We have 32 small MEMS microphones that are capable of capturing the sound that's coming from the leaks, and knowing the positions from the different sensors, we can pinpoint the exact location, the exact origin where the leak is making its sound. We also have an emitter, but that's not for this use case. That's for if we would like to navigate ourselves around the environment as a bat. Here we see the operator here in the corner. Here we see the augmented reality view with a set of pipelines that's located here on the board. In a second, we will turn on the compressor and generate some ultrasonic leaks. So here you see that the system is picking up these leaks as the operator is looking towards them. And if he puts his hands over the leak, the red circle disappears. Now you might have noticed that the leak is not perfectly on the location of that the red circle is not perfectly on the location of the leak. That's because the turbulence that's actually creating the whistling sound is not at the location of the leak. The air is spewing out of the leak and creating turbulence, and the sound is coming from the location of the turbulence. But using different measurements, we can then pinpoint the most likely location of these leaks, and that's already very helpful. So knowing this, we have validated our case. We come to air leak SLAM because while these systems work, the ultrasonic camera systems to detect those leaks, they work nicely, but they still require the operator to move around. And then we were thinking, is there another way to automate this process? Therefore, we implemented air leak SLAM, and we put our ERTIS sensors, the microphone arrays of the ERTIS sensors, we put them onto something that's already driving around in the factory, because most warehouses have small AGVs running around, or have forklifts that are driving around, or have small machinery that's always moving around the place. If we would design a system with an acoustic camera on it, we would be able to pinpoint the location while the car is already running and driving around. That would be useful. To make it even more intuitive, it would be useful to also put a LiDAR sensor on top of it and create a map of the environment that we're running, that we're driving around. That problem is known as SLAM, simultaneous localization and mapping. So we are simultaneously making a map of the environment while we are driving through it. This would allow us to, in the first step, make a map of the environment, and in the second part, as a bonus feature, all the leaks are indicated on the map, or where we estimate them to be on the map. We have done a small, we have several experiments with this, and I magnified the map for a bit. So this is the basement here on campus. We fitted it with piping that we run pressurized air through. So the orange lines that you see here are piping. Then the blue squiggly lines are the trajectory that the robot went through. The red dots indicate measurements, so where the robot estimates or where the robot thinks at one point there is a leak here. And the leaks, the actual leaks are indicated by the blue check marks or the blue X's. And the estimated leak locations are the green circles. Now, after we've done our run through the warehouse, we can take a look at all these points that we gathered throughout our measurements, and we can do some calculations on them, and we can take something like the average of this out of these measurements, and say, okay, in the center of all these measurements is our estimation for where the leak is supposed to be. And we can see that for leak A, B, and C, we have almost exactly pinpointed the location of that leak. Now, this is incredibly useful because this allows the company to every day, at the end of the day, to create a map of new leaks or existing leaks and check up on what is the leaking situation of your entire company. Instead of having one person do a yearly check and then risking the chance of several air leaks losing energy throughout the entire year. So this is a cost-saving measure because you don't have to have that one person driving around, walking around the plant. We can be busy doing other things, and otherwise the leaks will be situated much faster. And because the leaks are now all gone, you saved all that money and you can safely drive home in your brand new Audi A7, or the entire board with these energy prices can turn home in the Audi A7C. If you would be interested, because that was the presentation on air leaks, if you would be interested in this technology, we can do prototyping projects. Feel free to contact me, because the system as of now is not available for sale, because that's actually a finished product. It's still in the prototyping phase, but cooperation is always a possibility, and if that's of your interest, feel free to contact me. Now we have the Q&A slide, and I can also create a bit of advertising for the next session that will be on the 21st of November. That will be on energy optimal motion trajectories, and more information can be found on foundersmake.be or following the QR code. So I don't know if any questions were submitted to the Q&A.
Yeah, we have one question so far.
Okay.
Can these methods to detect air leaks also be used to detect leaks from other gases, for example, helium or nitrogen?
Yes, that is certainly possible. The only thing we noticed that might have a bit of an issue is liquids, because liquids tend to dampen the oscillations of the turbulence a bit. But as long as it's gases, that should be not an issue. The only thing that can happen if a gas is less dense or has a lower atom count, or how do you call it, that can change the pitch of the frequency. But if we know what gas it will be, and if we could do some test measurements, it's certainly feasible. If there's a specific use case for this, we will be more than happy to come and test it out at your plant, if you want to detect some other gases.
Okay, no further questions so far. Maybe we wait one more minute to see if there are other questions coming. I have a remark. It's a very short question. Distance limitation. Is there any limitation on the distance for tracking those leaks?
Yes, there is a distance. We won't be able to detect the leaks from 100 meters, except when it's a very big leak. But then you'd be aware of the leak before the sensor would pick it up, if you can detect it at 100 meters. Mostly the sensors have a range of about 10 to 20 meters, but that's very dependent on the actual size of the leak, because the bigger the leak, the louder the sound will be, or the more intense the leak, the louder the sound will be. So if it's a very small leak, it's obvious that you would have to get closer to the pipeline to detect the very small ones. But yeah, in terms of range, as long as it is within 20 meters, we should be able to pick it up. Also because we're driving around and taking measurements at, I think, 10 to 15 hertz, so 15 measurements per second. That's a lot of information, and the chances are high we'll pick it up at some point.
Okay, another question. What with vacuum leaks?
Vacuum leaks. So, for example, if a vat would be a vacuum inside and the air would leak from outside to inside of the vacuum, that is a good question. I think then the whistling sound would be on the inside of the vacuum tank. I do not know if we will be able to pick it up in that sense, because the sound is going into the tank, but that could be certainly worth investigating. Yeah, as long as there is some turbulence happening at our side of the tank wall, it should be possible to pick it up.
Okay, another question. Is there any impact of the air pressure or other parameters on the measurement methodology?
Can you repeat the question?
Is there any impact of the air pressure or other parameters on the measurement methodology?
No, the only thing that can happen is that we would need to change the parameters of our filters if the leak would be of that much diverging frequency to the ones that we used in the settings for these leaks. But that's something that, with some calibration, can certainly be fixed on the spot. On the spot, but if we know what to expect, it would be easier and we can make it a bit more robust for those specific locations.
Okay, another interesting question. May your production keep on running during these measurements?
Depending on the type of production, yes. Of course, we are working with ultrasound, so the measurements are sound sensitive. If you have a lot of other metallic noises nearby, for example, if there were power drills going on next to the microphone array, or you have some chainsaws, that can cause a lot of disturbance in the for the measurements, and it can make them a bit less, can make the estimations a bit worse. But we aim to try to tackle this by doing a lot of measurements. Like I said, we measure at 12 to 15 hertz. So chances are small that all these noises are consistently going on at the same spot. So if we measure 15 times a second, chances are high we pick it up at some point again, and then we can still pinpoint them. But loud ultrasonic interference can pose an issue. But that will will mostly be an issue if you have a lot of if you do a lot of metal working in your factory.
Okay, there are no more questions. We answered 5 of them, so I guess that it made some things clear, and it's time to wrap this session up. So I'll leave the floor to you to finish the session, Robin.
Okay, thank you. Thanks for the coordination, and I will end on this slide with my contact info. So if you have if you would like to have any more information on this system, or you would like to test it out in your factory, if you want to really get a good view of the vacuum tanks, if we can register the leaks, feel free to let me know. We can certainly arrange something. There's also the website of the research group and our 3D Sonar website. So I hope you enjoy the rest of the sessions. The next session is the energy optimal motion trajectories. And then I'll leave you with 5 minutes to grab your lunch.